Hello, physical science students. This is the promised screencast recording of the material for the rest of Chapter 10, dealing with chemical reactions. This is the material that's on the handout you got in class on Wednesday, April 6th, and that we didn't quite get finished. And this is example 15, and outdoor grills and some stoves and other devices for cooking use propane gas, which is C3H8 for the fuel. This problem has multiple parts dealing with the combustion of propane gas. First of all, what's the other reactant that's required for propane to undergo combustion? And as talked about before, for a fuel to burn or combust, it needs oxygen, O2. Second part, what are the products of the complete combustion of propane? And again, as we've talked about before, if we have a fuel that's made of carbon and hydrogen, and oxygen is needed, of course, for it to burn, when it burns, when it completely combusts, it makes carbon dioxide, CO2, and water, H2O. Okay, next, let's write and balance the reaction equation for the complete combustion of propane. So propane is C3H8. It requires oxygen, so we go plus O2, and then we put an arrow to indicate reacts to form, and then it forms CO2 and H2O, and that is our unbalanced chemical equation for the complete combustion of propane. Now we need to balance the equation, and we note that there are 3 carbons on the left of the equation. Therefore, we have to have 3 carbons on the right of the equation. We put a coefficient of 3. We have 8 hydrogens on the left of the equation. We have 2 hydrogens in water, so 2 times 4 gives us 8 hydrogens if we put a coefficient of 4 here, and that balances the hydrogens. We purposely did carbon and hydrogen first and left oxygen until last, because when we put coefficients in front of CO2 and H2O, that changes not only the carbon and the hydrogen respectively, but it also changes the oxygen. So we leave the O2 to balance last because we can put a coefficient here and that balances the whole equation and doesn't mess any of the other elements up. So on the right, we have 3 times 2 oxygens from the carbon dioxide, so that's 6. We have 4 times 1 oxygen from the water, so that's 4 more added to the 6 gives us 10. So that means the coefficient here needs to be 5 because 5 times 2 gives us 10. So now we have a complete balanced equation for the complete combustion of propane. Now D, how many molecules of O2 are needed to completely react with 7 molecules of propane, C3H8? And the key here is note what the balanced chemical equation tells us. It tells us that 1 molecule of propane reacts with 5 molecules of oxygen to make 3 molecules of carbon dioxide and 4 molecules of water. And that is the simplest number of molecules that can react. But of course, we could have lots more propane, but however many propane molecules we have, it's going to require 5 times as many as that oxygen molecules. It'll produce 3 times as many CO2 molecules and 4 times as many H2O. So if we have 7 molecules of propane, then the balanced chemical equation tells us that for every 1 mole of molecule of propane, it reacts with 5 molecules of O2. So we essentially have a conversion factor where for this equation, 1 molecule of propane needs 5 molecules of O2. And so we can do a conversion, converting from molecules of propane, which we have. We multiply by a fraction that gives the correct ratio of molecules of propane compared to molecules of oxygen. We put molecules of propane on the bottom of the fraction, and then in this case 7 times 5 gives us 35 molecules of oxygen that are needed. Now note, this you could probably just do in your head for this simple example, but I'm showing you the way you set this up in case the numbers were more complicated, and what would be sort of the general process to do this sort of conversion or calculation. Okay, E. How many moles of oxygen are needed to completely react with 7 moles of propane? Well, we previously did how many molecules of O2 are needed to react with 7 molecules of propane. And note that this 1:5 ratio that we used in the previous problem is true regardless of how much propane we have and how much oxygen we have. The ratio of the two needed for the reaction is always going to be 1:5. And remember that a mole is just simply a really, really big number of oxygen molecules. It's kind of like a dozen to a chemist. So if the question was how many dozen oxygen molecules were needed to completely react with 7 dozen molecules of propane, you'd say, well, 7 times 5 gives me 35 dozen for my answer. And the process is exactly the same if we use the chemist's dozen, because remember that a mole is just this very, very large number of molecules, 6.02 times 10 to the 23rd molecules. But if we have 1 mole of molecules of propane, we'll need 5 times that many moles of molecules of oxygen to react with it. So we can, again, you can do this possibly in your head, but let's set it up as an actual conversion. 7 moles of propane is what we have. The balanced chemical equation tells us that for every 1 mole of propane, we require 5 moles of oxygen to fully react. So do note the stoichiometry, these numbers, these coefficients balancing the chemical equation, are true for molecules, and they're also true for moles. In other words, 1 mole of propane reacts with 5 moles of oxygen to make 3 moles of carbon dioxide and 4 moles of water. So 7 moles of propane times 5 moles of oxygen per 1 mole of propane gives us the same number as before, 35, but it's now 35 moles of oxygen because we're dealing with moles in this problem rather than the molecules we dealt with in the previous problem, but the ratio is the same. Okay, so how many moles of carbon dioxide are produced by the complete combustion of 7.94 moles of propane? And we use the same process. We have 7.94 moles of propane, and now we want to know how many moles of CO2 are produced, and the balanced chemical equation says there are 3 moles of CO2 produced for every 1 mole of propane that reacts. So our conversion factor is for every 1 mole of propane, we need 3 moles of carbon dioxide. Moles of propane cancel if we set up our conversion factor properly, and 7.94 times 3 gives us 23.8 moles of CO2 that are produced by the complete combustion. 23.8 moles of CO2 are produced by the complete combustion of 7.94 moles of propane. Okay, now part G, how many grams of CO2 are produced by the complete combustion of 7.94 moles of propane? And notice we, in the previous problem, figured out how many moles were produced, 23.8 moles of CO2. So, if we have 23.8 moles of CO2, if we want to find out how many grams that is, we note that carbon dioxide, CO2, its mass of 1 mole is going to be the mass of a mole of carbon plus the mass of 2 moles of oxygen. And if you look up on the periodic table, the mass of carbon is 12.01 grams per mole. Mass of oxygen is just about 16, depending on which periodic table you use. It might be 16.00 or 15.9994. And we have 2 moles of oxygen, so it's going to be about 16 times 2. So that's 32 plus the 12 for the carbon. So 1 mole of carbon dioxide has a what we call molar mass, or weighs 44.01 grams. We're using a conversion factor again to convert from moles of carbon dioxide into grams of carbon dioxide, and that works out to be 1,047 grams of CO2 that's produced by the complete combustion of 7.94 moles of propane. And then 7.94 moles of propane, how many grams is that? And we use the same process we did in the previous problem, converting moles to grams. We need to determine how much 1 mole of propane weighs. And again, carbon is about 12, so 3 times 12. And hydrogen's about 1, so 8 times 1. And we add together the 3 times 12, which is 36, plus 8 times 1, which is 8. And use slightly more precise numbers from the periodic table. And what we end up with is 1 mole of propane has a mass of 44.09 grams. It's sort of coincidental that in this problem, the molar mass of propane is almost the same as the molar mass of CO2 that we used previously. That's just coincidence. In general, we'll have typically quite different numbers between molar masses of different substances. So we do that conversion, cancel the units, multiply out 7.94 times 44.09, and we get 350 grams of carbon dioxide. And now one thing we could do is we can tie this all together and notice that we figured out that the 7.94 moles of propane is 350 grams of propane, and we figured out that the amount of CO2 that was produced was 1,047 grams of CO2. So when the 350 grams or the 7.94 moles of propane undergoes complete combustion, it produces 1,047 grams of carbon dioxide. And notice here, by combining several steps, we could actually, if we wanted, start with mass of, let's say, a reactant in our chemical reaction and convert it to moles, then convert that number of moles of the reactant to how many moles of either, in this case, of product it would produce, and then convert that moles of product into that number into grams of product. And so via several calculations and conversions, we could figure out how much mass of product was produced from a given mass of reactant. And that should be enough for now. That finishes off this example and the remaining material from the Wednesday, April 6th lecture.